Hello everybody. In yesterday's session we saw about the star connection of three-phase systems, both three-phase 3-wire and three-phase 4-wire, and I also explained you about the unbalanced three-phase system in the star connection. Now we see a delta connection today. So here the first figure, if you observe, these are three single phase systems, okay, which can be generated by using three coils spaced 120 degrees apart on a rotor in a magnetic field and rotated in the counterclockwise direction at a constant angular velocity of omega radians per second. Now yesterday we saw that this three single phase systems what you have here can be interconnected for a three phase operation by connecting finish to finish, and all the three finishes of the phases can be connected together, and similarly on the load side all the second terminals can be connected together. So that will eliminate conductor 2, conductor 4 and conductor 6. So that gives us a three phase star connection. If the common point on the load side and the common point on the star side are connected together, we got a three phase 4-wire system. So that is the star connection. In case of delta connection, I can also reduce the number of conductors by interconnecting the systems. The way of interconnection of these phases compared to star connection, in delta connection it is a different way. So what I do here, I will be connecting finish of R phase to the finish of Y phase. So this is the junction what I get while connecting finish of R phase to finish of start of R phase, finish of Y phase to start of B phase. So these two junctions are there. So I just took two wires here. That means the conductor 2 and 3 here are replaced by single conductor, and 4 and 5 are also replaced by a single conductor, eliminating two conductors out of the 6th one. Now by connecting these three, what I am getting is B phase, Y phase and R phase, all three voltages in such a way that they are all in series here. Forget about the line what I have taken. Just by making the connection, I have all the three connected in series here. Now when I try to connect the fourth one like that, the third connection, finish of B phase to the start of R phase, I will be making a closed loop here. So unless all the three induced voltages in the three phases adds up to 0, I cannot connect this finish of B phase to the start of R phase. If I do so, then there will be a resultant voltage that causes a circulating currents inside the delta. Okay. Now this delta connection is possible without circulating currents only when the voltages ER plus EY plus EB at all instants added to 0. Okay. So when that happens, I can connect B phase finish to the start of R phase and take out another wire, okay, from this junction. So I have 1, 2, 3 wires taken from 3 junctions. Therefore this will be a 3-phase 3-wire delta connected system. Now there is no common point like star connection in this, therefore 3-phase 4-wire delta connection is not possible in this system. Okay. So this is what the explanation I have given here. Join R dash to Y, thereby replacing conductor 2 and 3, Y dash to B together replacing conductors 4 and 5 by single conductor. So before connecting to join the finish B to start R, we must make sure that the voltage is 0, otherwise there will be circulating current in the delta. So this definitely, okay, ER plus EY plus EB, because all three coils are identical in number of turns, conductor cross section, everything, okay. So I will have equal amount of voltages induced in these three phases with a phase difference of 120 degrees between them. So added together I will be getting the resultant as 0. Therefore it is possible to connect the finish of B phase to the start of R phase without any circulating current in the circuit, in the delta connection. Now I will see the voltage and current relationship in the three phase systems. Now if I see a star connection or a delta connection here, you can see between the terminals of a phase I will be getting a voltage, and between the terminals, between the lines, I get another voltage. If I go to a star connected system, the voltage what I get between the terminals of a phase and between the lines, okay, there is a difference. Similarly, in the delta connection, the current what you have in a phase and the current which is coming out of this junction, there is a difference. Okay. So, because of that, I need to find out the relationship between the voltages and currents in the three-phase system. Okay. Now, in any three-phase system, there are two sets of voltages, what we call them as line voltages and phase voltages, and there are two sets of currents, one is called as a line current and the other one is phase current. In the star connection also I will have a line voltage and phase voltage, line current and phase current. These four parameters what you have, two voltages and two currents, also exist in the case of a delta connected three-wire system. Okay. So, there is always a relationship between line voltage and phase voltage, line current and phase current in case of the three-phase circuits. Let us take a star connected system. Okay. Here on the slide I have not shown any diagram as such, but just because I am giving the explanations for these different voltages. Assume the EMF in each phase to be positive when acting from the neutral point outwards, that is the common point what you have R to N, N to R. This voltage ERN will be acting from N to R, then in that direction it is positive. Similarly, the second voltage acts from N to Y, therefore it is positive in that direction. Same way, EBN is positive when it is acting from that neutral point N towards the point B. So, these are three phase voltages in the case of a star connected system. We can measure the voltages between two lines in a star connected system. We call it as line to line voltage or simply line voltage, okay, or between a line conductor and a neutral point. So, in this, see that neutral point is not coming in the measurement of line to line voltage, the neutral point is not coming, whereas in measuring the voltage, the second voltage, I am saying that the voltage can be measured between a line conductor and the neutral. So, whatever voltage you are measuring between the line conductor and the neutral, that is called as the phase voltage, and the voltage what you are measuring between two lines, that is line to line, any two lines, okay, there will be line voltage. Okay. So, in a three-phase star connected system, R to N it is one phase voltage, N to Y the other phase voltage, N to B these are the third phase voltages. Therefore, three phase voltages will be there in this system. Similarly, between R and Y I can measure one line voltage, Y and B I can measure another line voltage, and B and R I can measure the third line voltage. Therefore, three line voltages and three phase voltages will be existing in star connected system. Similarly, the current what is flowing from N to R, that is called as the phase current, Y to N is the Y phase current, B to N to B the current in this B phase is called as B phase current. Now, these currents will flow out of the star connection through the lines, and the currents what we have in the lines we call them as line currents. Now, in the slide here what you can see is a star connected, okay, this is star connected generator, three lines are there, okay, and one neutral. Therefore, there are four conductors what I am using. So, the generator is a 4-wire generator here, one is neutral, the other three lines phases are there, okay, R, Y, B, N these are the terminals of the generator. These are connected through a three-phase load through 4 wires. So, this is a three-phase 4-wire system. If I measure the voltage between N to R, that will give you the phase voltage Rn, N to Y phase voltage Yn, Vyn, and B to N to B this is phase voltage Vbn measured at the terminals of the generator, whereas this ERN, EYN and EBN these are the induced voltages. Okay. So, there is a small impedance drop across each three phases, okay, because all the phases, all the windings are identical, the impedance is identical. So, the current what you have here IR, IY and IB they are also identical, that means they are symmetrical here, they have equal magnitude and a phase difference of 120 degrees between them. So, that drops given by these currents in the winding, subtracting those drops I will be getting the terminal voltages. Okay. I need to subtract the drops from the generated voltages ERN, EYN and EBN to get the terminal voltages VBN, VYN and VYN and VBN, VRN, VYN and VBN. Now see, in measuring this VRN, VYN and VBN, I am using the neutral point as a common point here. Therefore, I am measuring the voltage between a neutral and one of the phase, therefore I call it as phase voltage. This is the same circuit, I can also measure the voltage between RY, YB and BR. Okay. So, because I am measuring the voltage between two lines, I call it as line to line voltage. If you see this network, the current what you have here IR, which is coming out of the phase, will come out of this line. Okay, it will flow through the conductor, line conductor what I have connected between the terminals of the load and the generator. It is flowing into the load through that line. Okay, there is no change in the current what you have in the phase and what you have in the line. Therefore, in a star connected system, whether it is 3 phase or 4 phase, 4 wire, 3 wire or 4 wire, I always have that the phase current what you have is equal to the line current in the system. Okay. So, that is the relationship between the phase current IR and the line current IR. This phase current I can write it as IRN, it is from N to R, okay, and this is IR. There is only one suffix here, it says the current in the line R. Here IRN I can use, that says it is the current flowing from neutral point to the R, it is the current in the phase. Therefore, that is called as a phase current, this is called as a line current. So, in a star connected system, the line current IR and the phase current IRN both are equal. Okay. So, this is VRN is the RMS value of the voltage drop from R to N. Okay. This is the phase voltage of R phase. Like that, we have the 3 phase voltages. The term line voltage is used to denote the voltage between the lines. As I told you, VRY represent the line voltage between the lines R and Y. Same way, VYB between Y and B, VBR between B and R. These are the line voltages. So, here I show you a phasor diagram. Okay. Now, to determine the relationship between the line voltage and phase voltage of a star connected system, we make use this phasor diagram. Okay. It is very easy to analyze from the phasor diagram. Now, I just gave you a simple phasor diagram here. I am considering the R phase voltage as reference, okay, and then VYN, the Y phase voltage, okay, that is phase voltage here, it is lagging behind the R phase voltage by 120 degrees, and the phase voltage VBN, it is lagging Y phase voltage by 120 degrees. Okay. So, that will give you the system of phase voltages VRN, VYN, VBN. I will just show you on the board how to draw this diagram. Okay. It is very simple to draw. First, you draw the phase voltage VRN as a reference. Okay. It is along the reference axis. You can take it as a x axis. Okay. Then followed by the voltage vector VYN at a phase difference of 120 degrees, and the third voltage will be VBN this is at a voltage angle of 120 degrees with respect to VYN. Now, make sure that all the 3 voltages what I have drawn has equal length, otherwise they won't be symmetrical. Okay. So, we have a like this, fine. Now, to determine the relationship between phase voltage and line voltage, we are using this phasor diagram. Now, remember, in drawing the phasor diagram, we will be using only the RMS values of the voltages. Okay. I will not be using any generated voltages here, because I will not be able to reach into the winding. I have access only to the terminals of the generator, where I have an access to the terminal voltage than the generated voltage. Okay. Therefore, I will be using the RMS value of the terminal voltages RN, YN and BN, the phase voltages of the machine. Okay. Now, the same phasor diagram I am showing in this slide also. I have shown this VRN as the RMS value of the R phase voltage, okay, of RMS value of the voltage of phase R, Okay. Now this line is an extra thing with respect to the neutral line N, line R, okay, R line, phase R line, that is okay, no problem. The line voltage VRY is the voltage drop from R via N to Y. So this can be represented by a symbol VRNY. So I have to move from terminal R to terminal Y through the neutral terminal N, that is why I represented N in the center. Okay. So while doing this, I will moving, I get a voltage of VRN, that is the voltage across the phase R, plus VYN. Okay, I have written it as VNY because my direction of movement is different one. If you see this, okay, here to reach from R to Y, I started at the terminal R, move to N, from N I am moving to Y, but my voltage what I have is there VYN, but I want a voltage of VNY here. Okay. So adding these two voltages, what all you are getting within the path from R to Y through the N, I am getting that line voltage VRY. So I will be getting these two voltages VRN and VNY. Okay. Now this sum, actually I have a voltage of VYN, I do not have VNY. Okay. Now in the phasor diagram, when VYN is in this direction, it is positive. Okay. It is positive. So when it is negative, I need to invert that. So invert means I have to just rotate the vector by 180 degrees. So I am getting this VYN here. Okay. So on the board I show that when I rotate this vector by 180 degrees, I get my vector like this. This is my VYN vector. Okay, minus VYN vector, or I can also write it as VNY. I need to add VRN and VYN vectorially, VRN and minus VYN vectorially as per this equation. Okay, all these are all vectors. Okay, so therefore I should have represented this by block letters, fine, but I have not done so, saying that these are all vectors. Okay, I have already told you that in three phase system all the voltages, or in AC systems unless otherwise mentioned, all these voltages we have to consider them to be the phasors only with a magnitude and a direction. Okay. Now I am just adding this VRN and V minus VYN to get a voltage VRY. Okay. So this is what you have. Now all three phase voltages have equal magnitude. Okay. The set of phase voltages is VRN, I am taking the phase voltage of V phase at an angle 0, VYN again phase voltage at an angle of minus 120, VBN V phase at an angle of minus 240, which also can be written as V phase at an angle of plus 120. Okay. Now when I substitute these expressions in the line voltage expression for VRY, I have VRN minus of VYN. Okay. So the difference of these two, okay, V phase minus V phase at an angle of 120. If I convert this V phase at an angle 120 into the rectangular form, I will be getting V phase cos of 120. Okay. Now whether its sign is positive or negative does not matter, because cosine of an angle will be always positive. Now since I have a minus sign here, I use minus j sin 120 degrees. So cos 120 is 0.5 or 1 minus 1 by 2, sin 120 is root 3 by 2. So I just substituted in this expression. Okay. Now if you open the brackets, I will be getting V phase plus V phase by 2. So added together I will be getting V phase into 3 by 2, that is 1.5 plus j root 3 by 2. This will give you 1.5 plus j 0.866. Okay. Now if you try to calculate the magnitude of the line voltage VRY, see this VRY here, it is in the complex form. Okay. Therefore it has a magnitude which depends on both the parameters and an angle with respect to the reference, that also depends on both this root 3 by 2 and 3 by 2. Okay. So the magnitude of the line voltage will be VRY is equal to V phase square root of 9 by 4 square of this plus square of this will give you root 3 times V phase. So this is what the relationship between the magnitudes of line voltage and the phase voltage in a 3-phase star connected system. Okay. This relationship will hold good even for 4-wire system also, but the requirement is the system what we are considering should be a balanced system, then only this relationship will hold good. In a unbalanced star connected system, I do not get this relationship between line voltage and phase voltage, as line voltage is equal to √3 times the phase value. Now if I try to calculate the phase angle, okay, I know both the real and imaginary component. So for angle theta is equal to tan inverse of imaginary component by real component, so I will be getting 30 degrees. Okay. So therefore VRY I can write it as √3 times V phase at an angle of 30 degree. Same way I can also write VYB is equals to √3 times V phase at an angle 30 here, with respect to the VYN as a phase voltage, and VBR also I can write √3 times V phase at an angle of 30 degrees with respect to BN. When I write that with respect to R, my angle becomes, see here I will show you in the next diagram how to get that 150, 90 and all. See, I can also determine the relationship by using the geometry. Okay. Previously I told you about the analytical method, now I am using the geometry here. Okay. Now the equation does not change, the voltage equation what you have, VRY will be equals to VRN plus of VNY. So this will be VRN plus of minus VYN. Okay. So plus of VYN, I already drawn this plus of minus VYN. Now I have to add these two vectors. Okay. So for that I will be completing the parallelogram. Okay, right. I have shown you that the magnitude of VRN, magnitude of VYN both are equal. That means in this parallelogram what I am getting, all the 4 sides are equal. So since all the 4 sides are equal, as per the characteristics of this parallelogram, I have the longer diagonal and shorter diagonal bisecting each other. So therefore this angle is 90 degrees. Okay. Now you see here the angle between VRN and VBN what you have, this is also 120 degrees. Okay. Now when I invert or rotate the vector VYN by 180 degrees, the angle 120 what you have between VRN and VBN will get bisected. So this becomes 60. So when this is 60, this angle is also 60 degrees. Okay, 60. As the longer and shorter diagonals are perpendicular bisectors, okay, they bisect the angles also, therefore this angle now becomes 30 degrees. So this angle also becomes 30. The longer diagonal what you have represents the line voltage VRY. Okay. Taking this as origin, A as the bisecting point and B as the other end, in the parallelogram I can write OB is equals to 2 times OA. Okay. Now I have a right angle triangle here. If I call the point as C, OAC is a right angle triangle in which OA is the base, fine, OC is the hypotenuse. So this angle is 30 degrees. Therefore I can write 2 OA is equals to VRN phase voltage, that is OC cos 30. OC is nothing but the phase voltage VRN cos 30. Fine. So cos 30 what you have, see OB is VRY. So cos 30 will be √3 by 2, square root of 3 by 2. So 2 cancels, that will give us √3 times VRN. So VRY, it is the line voltage VL, and VRN is the phase voltage. Therefore, I have the relationship between magnitude of line voltage is equals to root 3 times the magnitude of the phase voltage. But you see the angle here. If I take this OC as reference, that is VRN as reference, when these vectors are rotated in the counterclockwise direction at an angular velocity of omega, VRY is always lying ahead of VRN by 30. So, in terms of vector, I can write VL, the line voltage, is equals to root 3 times V phase, okay, and it has an angle of 30 degrees, leading the reference by 30. Similarly, the other two line voltages, what you have, VYB, okay, VYB, which is obtained by using VYN and VBN, that leads the corresponding phase voltage, that is VYN, by 30. That means my VYB vector will be here, okay, 30. So when this is 30, as this angle is 120, 120 minus 30 will give you the angle between VYB and the reference vector VRN as 90 degrees, okay, 90. Similarly, when you try to get the third voltage VBR, now I can extend VRN in the reverse direction, it becomes minus VRN, add these two voltages, okay, I will be getting a line voltage VBR. That VBR will be leading VBN by 30, okay. So what you have, VBR will be having a magnitude of root 3 times VBN, but it is leading VBN by 30. So this angle of this VBR measured with respect to the reference is 120 here plus 30. So the total angle what you have here, it becomes 150 degrees. So what I want to say here, if I take a common reference, then my angle should be expressed with respect to that difference. Otherwise, I can also say that in a 3-phase star connected system, the corresponding line voltages, okay, or line voltages leads the respective voltages by 30 degrees, okay. Now as I told you, as I have shown you the diagram, in which I already told you that the line current will be equal to the phase current in the case of star connection, okay. Now this relationship will hold good whether it is a 3-phase 3-wire system or 3-phase 4-wire system. But this relationship what we are deriving, they are just for balanced circuits. Unbalanced systems, this relationship will not hold good, okay. Kindly you have to keep that in mind, okay. Now I will come to the delta connected system. In this delta connected system, I have 3 phase currents, okay. See, I R dash R, Y dash Y, B dash B. So these are the 3 phases. I R dash to R means the current is flowing from R dash to R, Y dash to Y is the current, B dash to B, okay, and they are assumed to be positive in the directions indicated by the arrows. I will show you the next slide what is the direction here. But one more thing is, when the load is balanced, all these 3 currents what I have given, they have the same magnitude, and I call that magnitude as the phase current I phase. So this is a delta connected system, okay. Now you can see here the current in the phase I R dash R is represented by an arrow pointing from R dash to R. That means this current is positive in this direction. Similarly, Y dash, okay, Y dash Y, what you have here, it is flowing from Y dash to Y in the Y phase. B dash to B, it is flowing in the B phase. So these are all the positive direction. When the currents act in this direction, they are considered to be positive, okay. Now I just measure the voltage available across R dash, okay. There is a induced voltage, there is an impedance for the coil. Considering the drop across the impedance, subtracting the drop from the induced voltage, the voltage what available at the terminals of this R phase, I call it as the phase voltage VRY, okay, R dash I can write, okay, I can write R dash, VR dash, but here because R dash is connected to Y, R dash can be replaced by Y, therefore I will be getting the voltage here as VRY. Similarly, the voltage what I will be measuring between Y terminal and the B terminal, I will call it as VYB, and the voltage what I measure between the terminal B and R, I will be calling it as VBR, okay. Now in this, the Y is nothing but R dash, so when I write R dash, it becomes the phase voltage of the R phase. If I replace Y R dash by Y, then I am measuring the voltage between the two lines, okay. So the same phase voltage what I am measuring across the winding, I am also measuring across the lines, okay, R line and B line, Y line. Therefore for the delta connected system, the phase voltage what you have will be equal to the line voltage, okay. But in finding out the relationship between the phase currents and the currents in the lines, okay, see the difference here. In the phase I am using double notation, double subscript notation here, R dash R, whereas in the lines I am using only single subscript IR. So when I use double subscript, it becomes a phase current, single subscript will give you the line current, okay. Now in finding out the relationship between the phase currents and the line current, I use Kirchhoff's current law. Now at this point what I call it as R, okay, because this is the start of the R phase, the finish of the B phase, I call the terminal as R here. At this point if I apply Kirchhoff's current law, I have sum of the incoming currents is equal to outgoing currents. You can see in the diagram IR is the outgoing current at this point, IB dash B is also the outgoing current, and the incoming current is IR dash R. So this current is equal to sum of these two currents, okay. Fine, that is what I have shown here. IR dash IR plus IB dash B, the two outgoing currents added together will give us the incoming current. So IR is the line current, it is expressed as difference of two phase currents, okay. Now same way here I have the relationship between IR and I phase current, the phase current, as IR is equal to the line current is equals to root 3 times the phase current. The same argument what I have given for the voltages can also be given for currents now, okay. What I have to do is, in this phasor diagram, if all the voltages are replaced by currents, okay, you replace VRN by IR dash R, VYN by IY dash Y, VBN by IB dash B, you will be getting the phasor diagram for the delta connection, okay. And the delta connection, as I see that the line voltage is equal to phase voltage, we need to identify the relationship between line current and phase current. So the same type of phasor diagram can be used, okay. Now if you see there, I just gave a analysis here, okay. I just mentioned here IR is equal to difference of two phase currents. You can use either geometric analysis or analytical method to prove this relationship, okay. For a delta connected system with balanced load, the magnitudes of the line current and phase currents are related by IL is equal to root 3 times I phase. Now again, if you see here, the line voltage in the case of a delta connection is equal to phase voltage and line current is equal to root 3 times phase current. This is quite reverse when compared to the star connected system. So if you see the important points about the 3-phase system, now all the problems or all the voltages what all mentioned in the 3-phase system, unless otherwise mentioned, okay, they will be line voltages, okay. Similarly, unless otherwise mentioned, the currents what they have given will be the line currents, okay. See the first line, it is this: for a 3-phase system, unless otherwise mentioned, it is normal practice to specify the values of line voltages and line currents. the current in any phase can be determined by dividing the phase voltage by its impedance. So, I phase is equal to V phase by Z, okay. And when you see the single phase circuits, we have taken the power factor to be the angle of the impedance, okay, whenever the voltage is taken as a reference quantity, or the power factor angle, it is angle between the voltage and current in the circuit, that also we can consider, okay. So, the power factor of Z, power factor angle we can write, or power factor of Z is same as the cosine of the phase difference between V phase and I phase. How do you calculate the power factor here? You can take the resistance and divide that with the magnitude of the impedance, okay. So, now in calculating the power factor of a three phase system, we consider the angle between phase voltage and phase current, right. We do not bother about the angle between line voltage and line current, we always take the angle between phase voltage and phase current in calculating the power factor, fine. These points you need to remember, right, for all the three phase circuits, this is very important, fine. Now, in the case of power, if you see in a balanced system, I just taking one phase, for a one phase the line voltage is V phase and the current, the voltage is V phase and the current is I phase. So, the average power consumed by this load is given by P1 is equal to V phase into I phase into cos phi. I am considering one phase of a three phase system, okay. The voltage what I am giving is the phase voltage, it is drawing a phase current. So, the angle between the voltage and current, what you have is phi, okay. So, this phi angle, it is also equal to the impedance angle of the load. So, therefore, V phase I phase cos phi will give you the power consumed, average power consumed by load 1, that is one phase, okay. As the load is balanced, that means all the three phases are identical, the power in the other two phases circuits will also be the same value. This happens only in the case of balanced loads, okay. It is only in the case of balanced loads. So, therefore, I am just calculating the power in one of the phases and multiplying it by 3, so that I will be getting the power in all the three phases, okay. So, P is equal to 3 times P1, 3 V phase I phase cos phi, okay. Now, depending upon star connection or delta, how this phase the loads are connected, I can modify this equation, okay. The modification will be in terms of phase voltage and phase currents without altering the power factor here, okay. Now, if I see here in a three phase system, it is normal practice to mention the line voltage and the line current. So, the total power in terms of VL and IL I should write, okay. Therefore, for a star connected system, we have the line voltage VL is equal to root 3 times V phase and IL is equal to I phase. So, in the expression for the power, that V phase I write it as line voltage divided by root 3, okay, and phase voltage, phase current I will be writing line current because they are equal, right. Phase voltage is line voltage divided by root 3, line current and phase currents are equal. So, these two modifications I did in this equation here. V phase I write in terms of line voltage, I phase in terms of line current, because those two are specified for us, okay. So, when I do that, 3 upon root 3 will give you root 3, okay, square root of 3 VL IL cos phi, okay. So, this is the expression for the power in case of three phase system. The same equation of 3P is equal to 3 V phase I phase cos phi, when applied to a delta connected system, I have in delta connection VL is equal to V phase and IL is equals to root 3 times I phase, okay. Now, making use of this relationship in the expression for power, I replaced V phase by VL and I phase by IL by root 3, okay. This is equation is modified, I phase is equals to 1 by root 3 times IL, that is what I have written. Again 3 upon root 3 will give you VL IL cos phi. So, for any balanced load connected either in star or delta, the total power is given by root 3 VL IL cos phi. So, it is a simple comparison between star and delta connections. Okay. This is also available in most of the textbooks also. I just compared around 6 points, there can be more number, but these are the very important one. Okay. Star connection and delta connection. If you see the star connection, I am connecting all the finishes there, therefore I say similar ends are joined together, whereas in delta connection I am connecting finish to start. Okay. Therefore, those are the unsimilar ends. Okay. So, here I should have written here unsimilar ends are joined together. This is not similar. Okay. I just copied and pasted it. I thought of changing it afterwards. I did not do that. So, this should be unsimilar ends are joined together. Okay. Then VL is equal to root 3 V phase and IL is equal to I phase. Here also there is a mistake, the typing mistake I have here. Root 3 phase, here it should be VL is equal to V phase and IL is equal to root 3 times I phase. This correction I will make you and afterwards. Okay. Neutral point is available, no neutral point is available in the case of delta connection. 3 phase 4 wire system is possible because there is a common point, and in the delta connection it is not possible as there is no common point. Okay. Both single phase and 3 phase loads can be handled in the case of star connection. So, that is possible when you have a 4 wire system. Okay. I can connect between one phase and the neutral the single phase loads, and between 3 phases I can connect a 3 phase load, whereas here it is not possible because the neutral point is not available. I can supply only 3 phase loads by using delta connection. Okay. By earthing the neutral wire, relays and protective devices can be provided in alternators for safety. Now, I do not have any connection like that in the case of delta connection, therefore, this is not available. Okay. Of course, compare this, just leaving the 6, the 5 points are very important. Okay. I need to make these 2 corrections, I will do it before uploading that. Now, measurement of power in the case of 3 phase systems, I need to use wattmeters in measuring. I always use wattmeters in measuring the power in AC circuits. Unlike DC the power is given by the product of voltage and current. There is no power factor in DC circuits, therefore, a voltmeter and an ammeter is sufficient to measure the power. Whereas in case of AC circuits, because I need to consider the angle between cosine of the angle between voltage and current in calculating the power, it is not sufficient for me to measure the voltage by voltmeter and measure the current by ammeter, taking their products. I can't call it as the real power or average power, because in AC circuits the average power is different than the apparent power. If you measure the voltage and current by using voltmeter and ammeter, take the product of that, you will be getting only the apparent power. The product of ammeter reading and voltmeter reading will give you apparent power, whereas if I use a wattmeter, it measures the average power, therefore it gives us power directly. So, by using a wattmeter, I can measure the power in 3 phase circuits directly. So, there are 3 methods of measuring power. One is the 3 wattmeter method, second one is 2 wattmeter method, and the third one is 1 wattmeter method. Now, the 3 wattmeter method, it is a direct method because I have 3 phases. I need to connect 3 wattmeters, 1 in each phase. So, adding all the 3 wattmeter readings, I will be getting the total power as the power consumed by the load 3 phase. I need to add all the wattmeters because wattmeters are showing average power. It is just sufficient to add them directly, just the magnitude addition. Okay, it will give you the total power consumed. Now, the 2 wattmeter method, if I see here, I will be just using 2 wattmeters, and some of these wattmeter readings I will be taking as the power consumed by the 3 phase circuit. And you see, as the 3 methods, if you compare the 3 wattmeter methods, I need 3 wattmeters, 2 wattmeter method is 2 wattmeters, I need 1 wattmeter method. Okay, I also have 1 wattmeter method where I will be connecting only 1 wattmeter in the circuit. If I am using this method, the requirement, that is, if I am going to use only 1 wattmeter in the circuit, the requirement is the 3 phase circuit should be balanced. otherwise I cannot use this 1 wattmeter, single wattmeter is not possible. Okay. As I told you, in the 3 wattmeter method, 1 wattmeter is inserted in each phase, each of the phase. The power consumed by the load is the algebraic sum of the 3 wattmeter readings. This is a straightforward method. Okay. The only requirement is to connect this, I should have the neutral point availability. If the neutral point is not available, then this is not possible to measure. Okay. This is not possible to use. So, if the neutral point is not there, so we can forget about that 3 wattmeter method. As I told you about, this is 1 wattmeter method. You can see this is a wattmeter. Wattmeter will have 2 coils, a current coil and a voltage coil, or we also call it as a potential coil. Now the current coil will carry a current what the load is carrying, therefore the current coil should be always connected in series with the load. Okay. And the potential coil will be carrying the voltage what I am giving to the load, therefore this should be connected across. Okay. Across, that means not series, parallel. Across is parallel, I should connect across the phase R and the neutral point. See, this 1 wattmeter method also, it is applicable even when I am not using, the neutral point is not available, but I have shown only one diagram here. Okay. I can give you the other diagram also. Now I will give you that later, but before that I will give the explanation for this part. The current coil of the wattmeter is connected in one line and the potential coil is connected between that line and the neutral point. So between here and the neutral point it is connected. So what it is reading, it will take the potential coil will take the voltage what I am applying to the load L here. Okay. That is, it will take the phase voltage. Okay. It takes the phase voltage and the current coil is carrying the phase current. So the product of the voltage, current and the cosine of the angle between the voltage and the current will be calculated by the wattmeter and it gives us the average power, as the power in a phase will be V phase, I phase, cos phi. So that will be indicated here. Now I told you here the total power will be 3 times the wattmeter reading, right. Now that happens, this happens only when all the 3 loads are identical. Okay. All the 3 loads are identical. Therefore, if one load consumes certain amount of power, the other 2 loads also consumes the same amount of the power. Therefore, that makes us easy to calculate the total power by using this expression. Okay. So that is what I told you the last line. This can be used to determine the total power consumed by a star connected balanced load with neutral point accessible. If I want to have a connection like this, I need to connect only the voltage potential coil across the R and the neutral point. Okay. Now without connection and connecting the neutral point also it is possible to measure the power using a single wattmeter method. Okay. This I will tell you when I am when I explain you about the wattmeter readings. Okay. How to calculate the wattmeter readings from the phasor diagram. I will tell you about how to use the single wattmeter method to measure power in the case of unbalanced load also. Okay. Thank you. So in the today's session we saw about the interconnection of the phases to get a delta connection, and we also studied about the power measurement, method of power measurements and the relationship between the line voltages, phase voltage, line current and phase current in case of 3-phase star connected and delta connected systems. So next session I will be doing some problems about these 3-phase circuits, and I also tell you about the measurement of power, detailed way measurement of power using 2 wattmeters. Okay. And I try to do the equations for the wattmeter readings, and I also give an expression for measuring the power factor in case of the 3-phase circuits using 2 wattmeters. Thank you.